Welcome to this Chemical Kinetics Masterclass. Today, we are going to dive into the fascinating world of reaction rates and gaseous systems. This first image sets the stage. We have a reaction occurring in a closed vessel, and we are monitoring it using pressure measurements. Let's get started. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Exercise 2. At time t equals 0, and starting from this moment, the temporal tracking of the evolution of the pressure P in a closed vessel commenced. 1. Calculate the value of A, the initial amount of substance of N2O. 2. Set up the progress table for this reaction, then determine the value of the maximum progress, Xmax. Exercise 2. Continued. 3. Give the expression for the total amount of substance of the mixture, N, at time t as a function of A and the reaction progress, X. 5. A. Determine the maximum pressure of the mixture. B. Deduce the half reaction time, T1/2. Note: question numbering faithfully reproduces the original source document. Let's break down the chemistry of our problem. First, we look at our reaction. 2 moles of nitrous oxide, N2O, gas, decompose into 2 moles of nitrogen gas, N2, and 1 mole of oxygen gas, O2. Notice the stoichiometry. For every 2 molecules we lose, we gain 3, 2 plus 1. This means the total number of gas molecules in our container is increasing, which is exactly why the pressure goes up. Next, we have our experimental conditions. It's crucial to be precise with units. Our volume, V, is 3 liters. But for the ideal gas law, we convert that to 3 times 10 to the minus third cubic meters. Our temperature is a hot 600 degrees Celsius, so we add 273.15 to get 873 Kelvin. Finally, we have our gas constant R. These are the tools we'll use to bridge the gap between what we see and the math behind it. Why do we measure pressure? Because we are clever. We cannot see individual molecules disappearing, but we can measure the pressure they exert on the walls of the flask. Think of pressure as a visible proxy for the reaction's progress. At the very start, T equals 0, before the reaction begins, the pressure P0 is 100 kPa. This is our baseline. It represents only the starting material, N2O. As the reaction proceeds and produces more molecules of gas than it consumes, the pressure steadily climbs. By tracking this increase, we are effectively watching the molecules transform in real time. It's like having a superpower. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's tackle question 1, finding the initial state. We use the famous ideal gas law, P0V equals ART. Here, A is just another name for N, the number of moles at the start. Step 1, rearrange the equation to isolate A. We get A equals P0V over RT. Step 2, plug in our values. This is where the anatomy of the equation is key. We must use pascals, 100 times 10 to the third, cubic meters, 3 times 10 to the negative third, and Kelvin, 873. Step 3, solve. The math gives us approximately 0.041 moles, or 41 millimoles. We've just calculated exactly how much matter we started with just by looking at a pressure gauge. Brilliant! Now, for question 2, the reaction progress table. Think of this as chemical bookkeeping. We track 3 states. 1, the initial state, x equals 0. We have A moles of reactant and 0 products. 2, the intermediate state, x. The reaction is happening. Stoichiometry tells us the pace. For every x moles of O2 formed, we must have formed 2x moles of N2. Simultaneously, 2x moles of our reactant N2O must have been consumed, leaving us with A minus 2x. 3, the final state, Xmax. This is when the reactant is completely gone. We just replace x with Xmax in our expressions. This table is the map that will lead us to the finish line. Where is the finish line? Since N2O is our only reactant, the reaction stops the moment it's all used up. This is our limiting reactant logic. Mathematically, we look at the final amount of N2O from our table, A minus 2x max. We set this equal to 0 because that's when the reaction is done. By solving for x max, we find that x max equals A divided by 2. Since we found A to be 41 millimoles, x max is exactly half of that, 20.5 millimoles. This value is vital because it represents the maximum extent or progress our reaction can ever reach. Question 3 asks for the total amount of matter N at any time t. To find this, we simply sum up the moles of every gas present in the flask from our intermediate state table row. N total equals N of N2O plus N of N2 plus N of O2. N total equals A minus 2x plus 2x plus x. Notice how the 2x terms cancel out. We are left with a beautifully simple equation. N equals A plus x. Check out the pedagogical note on the right. Why does it increase by exactly x? Imagine 2 molecules of N2O breaking apart. They are replaced by 3 molecules, 2 of N2 and 1 of O2. That's a net gain of 1 molecule for every unit of reaction. It's like exchanging 2 $5 bills for 3 $5 bills. You end up with more items than you started with. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Question 4. Linking the states. This is the most elegant part of the process. We have 2 snapshots of our system. State 1, time t equals 0. Pressure is P0 and moles N equals A. State 2, time t. Pressure is P and moles N equals A plus X. We write the ideal gas law for both. Equation 1, P0V equals ART. Equation 2, PV equals A plus X RT. We want to find X as a function of P. By setting these 2 equations next to each other, we can use their shared constants, V, R, and T, to create a bridge that connects our physical measurements to the chemical progress. Let's build the mathematical bridge. Step 1, divide equation 2 by equation 1. This is a pro move because it makes everything constant just vanish. V, R, and T all cancel out. Step 2, simplify. We get P over P0 equals A plus X over A, which splits into 1 plus X over A. Step 3, isolate X. We move the 1 over and then multiply by A. This gives us X equals A over P0, P minus A. Step 4, substitute our known values. The term A over P0 becomes a constant alpha equal to 4.1 times 10 to the negative 7th. Our final bridge equation is x equals 4.1 times 10 to the negative 7p minus 4.1 times 10 to the negative 2. This is powerful. If you tell me the pressure, I can tell you exactly how many moles have reacted. The invisible is now visible. Question 5a. Predicting the maximum pressure. Now that we have our bridge equation, we can look into the future. At the end of the reaction, X will reach Xmax. At that exact moment, the pressure P will reach its maximum value, Pmax. Using our formula, we rearrange it to solve for Pmax. Pmax equals Xmax plus 4.1 times 10 to the minus 2 divided by 4.1 times 10 to the minus 7. When we plug in Xmax equals 20.5 times 10 to the minus 3 moles, the math leads us to 150,000 pascals, or exactly 150 kilopascals. This is our theoretical ceiling. Even without letting the experiment run forever, we know exactly where that pressure curve is heading. Isn't that amazing? Question 5b. Defining the half-life. The half-life, T sub 1/2, is the time it takes for the reaction to get halfway to the finish line. In terms of progress, it's when X reaches Xmax divided by 2. To find the half-life from our graph, we first need to know what pressure corresponds to that halfway point. Step 1. Target X equals 20.5 times 10 to the negative third divided by 2. Step 2. Plug this back into our bridge equation to find the target pressure. The calculation gives us P sub 1/2 equals 125,000 pascals, or 125 kilopascals. So to find the half-life, we don't look for half the pressure, 75 kilopascals. We look for the pressure that corresponds to half the progress, which is 125 kilopascals. Let's find it on the graph. Final step. We use a graphical determination to find our answer. Take your pen and find 125 kilopascals on the vertical pressure axis. Draw a horizontal line until you hit the blue experimental curve. From that point of intersection, drop a vertical line straight down to the time axis. Where does it land? Right at 60 minutes. So T1/2 equals 60 minutes. We've done it. We used physics, math, and chemistry to determine the fundamental speed of this reaction. You should be very proud of this systematic analysis. Before we continue, dear friends, don't forget to subscribe, like, share the video with your friends, and also leave comments to encourage us to continue making this kind of content. Let's look back at our methodological flow. This is the how-to guide for any kinetics problem using pressure. 1. The visible proxy. We start by measuring something we can see, like pressure over time, P of T. 2. The gas physics. We use the ideal gas law, PV equals nRT, to relate that pressure to the total amount of matter, N. 3. The chemical bookkeeping. We use our ICE table to relate that total matter N to the specific reaction progress, X. 4. The kinetic marker. Finally, we build a mathematical bridge to locate important milestones, like the half-life. This workflow is your roadmap to success in chemistry. Master this, and you can solve almost any problem. Here is our synthesis results matrix, the big picture of everything we've discovered. A equals 41 millimoles, our starting point, the initial amount of reactant. Xmax equals 20.5 millimoles, our capacity, the maximum extent the reaction can reach. Pmax equals 150 kilopascals, our destination, the final pressure at completion. T1/2 equals 60 minutes, our pace, the time it takes to reach the halfway point. These 4 values fully describe the story of our chemical reaction from beginning to end. Look at how much information we extracted from just a simple curve. Finally, let's look at the core philosophy of our lesson. Chemical kinetics is all about bridging the gap between two worlds. On one side, we have macroscopic reality, things we can measure in the lab, like the pressure P at any time t. On the other side, we have microscopic reality, things we can't see, like the individual moles X reacting at any time t. The ideal gas law is the key that unlocks the door between these worlds. By understanding the boundaries, where we start, initial boundary, and where we end, final boundary, we gain a complete understanding of the reaction state at any moment. Never forget, science is the tool that lets us see the invisible through the lens of the measurable. Keep questioning, keep calculating, and keep being curious.